And I'm back at it for more, just like you. Hopefully you're watching this and you're feeling a little more refreshed than I see that I look. I had to take my son out driving a little bit today. That does take some years off your life. He just has a permit, and we got to get that license, man. So, a little nerve-wracking. But anyway, we are going to finish this chapter. So you are now looking at Chapter 3, Lecture 3. We only have one topic left to talk about, and those are the active processes involved with transporting across a plasma membrane. So at this point in Lecture 1, sorry, I got to itch my eyeball. We covered, and scratch my nose. We covered the plasma membrane, the components. Look at all those chapter learning objectives that are on Wiley Plus. We'll jump over to that when I'm done. But there were components, questions associated with the plasma membrane, and then all of the different types of passive transport. We had simple diffusion, we had channel-mediated facilitated diffusion, we had receptor-mediated facilitated diffusion, and then osmosis, the movement of water. So my nose is really itchy. Sorry, guys. I just can't wait. So those were all movement along a concentration gradient. Water follows salt. That's the golden rule. Goes to the party. Don't forget that, and you'll always get those questions right. So what we have to talk about today are active processes. And if you remember, active processes involve the use of ATP. ATP is the only form of energy that a cell can use. So it's all about making more ATP so that I can do these cellular processes because they're kind of important. All right, so I'm going to jump to the PowerPoint while I'm kind of pretending to stare at you. I'm not really. And, I got to make myself tiny. Okay. And, okie dokie, what do we have here? So let's finish this chapter with what, nuts. Oh, okay. With what we have to talk about. And then we will, should I be on this part? No. We'll go to the Wiley Plus and look at those learning objectives, because the next thing you have after you complete this last lecture in Chapter 3 is an exam. And that's coming up. So, okay. So active transport is typically, when you move something against its concentration gradient. So if it's against its concentration gradient, of course my dog is barking. I'm not winning here, people. That means it's going from where it's low and it's moving to where it's high. So that's not natural, right? That's going against the flow. And because of that, we have to use energy, and our energy is in the form, hey, come on, pencil. Is in the form of adenosine triphosphate. That's ATP. I'm going to have to yell at her. Okay, so there are 3 types of active transport. I'll use ATP. Well, I say 3 types, but then there's all these subtypes. So there's 3 major categories. Oh yeah, look, it even says major types. There's primary active transport, and that is going against a concentration gradient. Pretty straightforward. We'll see that in a minute. Sorry about the dog, guys. It's just going to be that kind of a day. Then there's secondary active transport, and that is kind of like the primary. So one with a little circle, that means primary. And, kind of like plus dessert. It's that one with a little more added to it. Can you tell it's after dinner time? And then the third major type, where's my pen here, people? Here it is when I have to move big things. So it's bulk transport. Bulk transport means move. Nope. Let me push this thing up a little bit. My little writing pad. Trying to figure that out so that I don't suck forever. But I guess I'm going to. Bulk transport when I need to move bit. I'm snarfing. I'm getting aggravated. Move big thing. things. And that is supposed to be the word big. It's the best I got. If you guys have any other ideas of what's using these tools, I will take it. Okay, so let's see what we got going on here. Primary active transport uses ATP, right? That's my cellular energy. I am going against a concentration gradient, and the main example we have of primary transport is the sodium-potassium pump. So the sodium and potassium pump, well, ATPase pump, I don't call it that. Oh, you'll ever hear me call it sodium, potassium, and then the pump. Involves moving two ions, sodium, which is Na, and then potassium, which is K+. So let's check this out. There is 3 steps to it. So this is primary active transport. And here is, I'm going to just look, well, since I said active, I'm using ATP. So when I use ATP, I break it down into a phosphate and then adenosine diphosphate. That's why it goes to ADP. And the fact that I'm using this creates energy to do work. Okay. Well, you guys heard what I said. Creates energy to do work. How come sometimes it works fine and if I can't? I'm all right, you know what I'm trying to write. Okay, so the first thing is, so this is outside the cell, extracellular fluid, that's outside cell. And then on this side, where it's kind of this funky little pink, if you're in color, is inside the cell. And this is saying that there is more sodium out, more outside, less in. Okay. And also it's saying that there's more potassium in. That's what this guy is saying here. And then there is less potassium outside. So that's my concentration gradient. Well, what am I going to do? I am going to take 3 sodiums from inside the cell, right? Because this is inside. And it's going to bind with an integral protein because it's spanning the entire I don't know, like distance across the plasma membrane of my phospholipid bilayer. So I have my integral protein. And it's going to bind 3 sodiums. All right, so when this binds the 3 sodiums, it will also trigger ATP to split. And as a result of it splitting, this protein changes shape, so it goes from being open to the inside to being open to the outside, and I spit out my 3 sodium, okay? Moves them to the outside. So then when it's open to the outside, 2 potassium, now remember, there's more potassium inside the cell, right? So there's more potassium in. And what am I doing? I'm grabbing another 2, and I am now bringing them into the cell. So I've used ATP, I've used energy to pump 3 sodium out where there's more sodium. Oh, kind of talked about this already. Okay, 3, that's supposed to be an Na and then a little plus. And then I have brought 2 potassium in to cell where there's more. So let's talk about that for a second. After I finish writing this. Something just happened. Okay, so, and that's just what the words are saying here. I'm bringing more potassium inside the cell. So because I have, now with this, using ATP, I'm getting a whole lot of sodium outside, right? And less sodium inside. And I'm getting a whole lot of potassium inside. And less potassium outside. So what does sodium want to do? I keep pumping it outside the cell. It wants to go in the cell. And I'm going to let it go in the cell, but only when I'm going to control. So now, let's see, because a ton of sodium outside, I control when I let sodium back in. And I control it, I make it do work, right? Make it do work. This control of letting it come in, and we're going to see that later on in the semester. But let's see. So I'm pumping a ton of sodium outside, right? So 1 ton of sodium outside. And then 2, I'm pumping 3 pluses out and bringing 2 pluses in, right? So there's going to be more plus outside cell. Oh, buddy. What did I just create if I have more of an ion outside the cell and more of a certain charge together? I've run out of room to write it, so I'm going to write it all the way down here. Together, because there's more sodium outside than in, there's more pluses outside than in, I have created electro. I was hoping somebody would say it. Maybe you said it in your head. Maybe you said it out loud. I created an electrochemical gradient, and I can only do that via the sodium-potassium pump, okay? Hey, by the way, that's a test question, because I love it. This is a tricky concept. It separates the men from the boys. I don't know, the girls from the girls, whatever. It's a tricky concept. So let me know if you want to talk about that further. All right, so that's one form of an active process that uses ATP to move an ion against its concentration gradient. Now, remember I said secondary active transport is kind of like primary plus desert. So what I do is I have one primary will get the sodium outside the cell. So secondary has 2 parts, kind of like, let's say that, has 2 parts. The first part is that I now have a lot of sodium outside the cell, right? A sodium gradient. What does sodium want to do? I already told you. Well, sodium totally wants to come into the cell, but I'm going to couple it with, it's like, oh, hey, you're going outside. Well, bring the garbage out with you when you go, right? Couple it with another action, with a second action. And this second action is moving another chemical, moving another molecule. I guess we could say molecule. That's a good word. It's not that I didn't prepare for this. I just don't think about this nitty-gritty. So I have 2 different types. So first there's 2 parts to it. We're going to let it go because there's not a whole lot to this chapter. Okay, 2 parts. So that was the 2 parts. Is used to drive it. So I am, because I'm then going to let sodium do what it wants to do, it's going to force another ion against its concentration gradient. You know what? I never really noticed that before. Because I don't really talk about this too much. So antiporter means that as sodium is coming in, the other guy is moving out, so it's in opposite directions. I'm trying to find like an example in my head of when I'm trying to make sense of that with you. It's like I let all the cats, I open the door in the morning, all the cats go out, right? So, well, I guess that's along their concentration gradient. But that would like, forget it. I can't think of it. Okay, so antiporter is an active transport, 2-part process, but then the desert is when I let sodium come back in, calcium goes opposite. The molecule, the ion, will go in another direction. So the other, oh, son of a biscuit, get me back to that. The other type of secondary active transport is a symporter, and symporter means both will move in the same direction. So let's check this out. How come sometimes this pen works great? So I have used the primary active transport and gotten sodium outside. Sodium outside via primary. I'm just going to call it active transport. Now sodium is going to come back in, and as it comes in, it's going to bring glucose in with it, which is against its concentration gradient, right? That's kind of the kooky part of it. But they're both moving in the same direction. So that's important. All right. So I had primary active transport, the sodium potassium pump, and then with secondary, there's two parts. There's the antiport, meaning when the second guy moves, he moves opposite sodium, and there's a symport, meaning the second guy will move in the same direction. I don't know. It's important to the body, but it's not that interesting. I like this guy a little bit more. It's my moving of big things. It's my bulk transport. Okay, so bulk transport means I'm moving big stuff. Right. And I'm moving it by wrapping it around, creating a little closet for it out of the plasma membrane, but we'll see that in a minute. So there's 3 different types of bulk transport, major types of bulk transport. I have either I'm moving stuff into a cell, and I have 3 different types. I have receptor-mediated endocytosis. Phagocytosis, oops, I was doing B, and you guys, my son did my laundry. I'm very impressed. And then I have penocytosis. We'll talk about that in a minute. So one type is moving stuff into a cell. That's endo, because endo, that prefix, is in. And then cyte is cell. So then the other one, exocytosis, because exo means out, like exit. It's moving stuff out of a cell. I don't have much to say about that. And the third one, which is not much else to say, is when I am just moving things across a cell from one side to the other. That's like my son rearranging his room. There's a whole lot of transcytosis going on with that bed. First it's here, then it's there. And I've used a lot of energy, right? So this bulk transport is using ATP. So it's an active process. Okay, so don't forget that, because I'll say, hey, what's an example of an active process? And you'll be like, oh, no diffusion. And I'll be like, no, it's not diffusion at all. It's passive. But bulk transport, endocytosis, exocytosis, transcytosis. I mean, you could answer it with like 1, 2, 3, and then even these subparts, 4, 5, 6 different answers to give for that. Well, and then you had primary and secondary. Okay, we're moving on. I'm not going to start with receptor mediated. I am going to start with phagocytosis, because phagocytosis is also known as, although I'm not a fan of this, cell eating. Okay, who does this? White blood cells do this. They engulf bacteria. So if you look at this awesome little picture here, I mean, how cool is that? This is a big old white blood cell, and it is engulfing a yeast cell. It's taking it in. So now let's go to this picture to talk about what's happening. So I have a white blood cell with its plasma membrane, and what it does is it kicks out these projections. These projections are called pseudopods, right? They are plasma membrane. I'm just going to say plasma membrane projections. Okay, and they wrap around it. So it wraps around. Here I have a little bacteria, a little microbe, and it's detected it, and it said, oh, I am going to wrap around you. So when I wrap around you, I'm totally not done. It's enclosed in a vesicle, okay? This vesicle is bound, so I guess I should say enclosed in vesicle, is bound kind of by its own plasma membrane. I'm just going to say PM, because you know if I write that out, it's going to take forever. It's by its own plasma membrane. So now it's in the cell, and it has this nice little cozy closet that it's hanging out in. You'd think it'd be safe. but it's not, because inside my cell, I have these things that are called lysosomes, and I call them packets of nasty. Okay, what they have is they are chock full of little chemicals, little enzymes, peroxide, and they're little packets of nasty. That was supposed to be a K. And these two fuse together, so it's a fusion. They fuse together, they join together, right? That's what fusion means, to join up. And then all that packet of nasty will just destroy this bacteria. And he's like, I was so comfortable. Not anymore, buddy. And then it's just garbage. And can kick it back out into the cytoplasm, or get taken care of by the liver or whatever. So that's phagocytosis. I love phagocytosis. Another form is of bulk transport. So remember, although I'm not showing you where the ATP is being used, it uses ATP, just like the other one. I didn't really say that. Okay, this uses ATP. All right, let's go back to this guy. Just like this one. So pinocytosis, instead of me putting out those pseudopods, there's no pseudopods. There's no little projections. But what happens instead is there is kind of an indentation. Indentation. It goes in, like the plasma membrane just kind of goes in plasma membrane. So whatever's out and about falls into that little indentation, and then it's just kind of brought around whatever into its own little vesicle, right? Bound by a plasma membrane. Now I know why he did my laundry, because they're out riding four-wheelers like a bunch of nutters. I'm so glad they're staying nice and quiet for a while I'm recording this little lecture for you guys. And then again, it fuses with my lysosome that has this little packet of nasty, and it dissolves whatever it brought in. This is very non-specific. This is like, I'm just kind of opening up, and whatever falls in there, falls in there. Who knows what it is? Very non-specific way of bringing whatever, right? This is just whatever into the cell. So it's like whatever comes into the cell, and then whatever gets dissolved into, I don't know, whatever bits. So let's look at this other one. This one is receptor-mediated endocytosis. So I'm bringing stuff into the cell. It's really like receptor-mediated pinocytosis, because I'm not engulfing it. I'm forming an indent around it, but this is kind of cool. So the first thing I have, I'm going to walk through this. Don't worry too much about the specifics. I don't care about the specifics, but I do care about this process. Just kind of understand it as a process. How is it different? Oh, son of a biscuit. Come on, you. How is it different? Oh, my goodness. Pinocytosis, all right? So what I have is I have these little receptors on my plasma membrane surface. And these little receptors are very specific. If I'm a receptor, I'm very specific. I only recognize one thing. That's like saying, I am only going to drink Coca-Cola. I'm very specific. I'm a Coke fan, so that potential exists. And nothing else. Water, lemonade, no. I will only see and bring into my body Coca-Cola. So my receptor is specific for Coca-Cola. Well, when I get Coca-Cola, all right, instead of it being an LDL particle, let's do something a little more interesting, like, okay, Coca-Cola. When it binds, that will trigger it to kind of form an indentation. Here I'm calling it an invagination. I don't care, an indentation. And then it will form a vesicle. So this is a vesicle. Who cares about all this clather and coat? I don't even care about half this stuff. I will get a vesicle. It is chock full of Coca-Cola. And whatever I need to do with it, I guess ultimately I'll bind it with a lysosome and dissolve it with my packets of nasty. I don't care about the specifics, but I do care that you guys see that I will only bring a very specific thing into the cell. Okay, so that's the difference, is that I have receptors and they have to find what they're looking for in order for any of this action to happen. That's kind of it. Okay. Exocytosis is just that I'm going to make something like a hormone in my Golgi apparatus. Who cares? We're not even learning that right now. Where's my pen? Okay, there it is. I'm going to make something and then I'm going to dump it outside the cell. So extracellular, remember, means outside the cell. I'm going to dump it into that extracellular space called interstitial fluid, and hopefully it'll get picked up by something. Or maybe, into the bloodstream. Oh, I can't spell blood when I'm trying to write it really tiny. Or it'll go into a duct like sweat, right? And oil. And then transcytosis is just moving something from one side of a cell across it. Oh, and then it's even saying out. Nah, I don't have too much to say about that one. Okay, so this table, which is rather helpful, gives you an overview of the passive processes. So I had diffusion, and diffusion was simple diffusion and facilitated diffusion. But remember, I have two different types. I have channel-mediated facilitated diffusion or carrier-mediated facilitated diffusion. So there was two different types. Okay, and then I have osmosis, and osmosis was the movement of water. And you kind of want to know that water goes to the party. Can I write down here? Oh yeah, water goes to the party. Okay. My active processes. I have active transport where I am moving something against its concentration gradient, either primary, that would be like my sodium potassium pump. We'll be using ATP, and then I had secondary, and secondary is where it's coupled. It's like, yeah, I'll take that special because it comes with the main entree and the dessert, and it can either be moving in the opposite direction of an antiporter, moving in the same direction as a symporter across the membrane. Remember, all of this has to do with across the membrane. And then I had my bulk flow. Is that on another one? Okay. Oops. And my bulk flow was bringing stuff in, bringing stuff out, bringing stuff across. Bringing stuff in, I had phagocytosis. I had endocytosis, where I'm just taking in whatever I can. And then I had the very specific of bringing stuff in that was receptor-mediated endocytosis. This is very specific. I wouldn't worry too much about ligands. We're not going to talk about ligands and clathrin-coated pits, but it's just about bringing very specific stuff in because I have a receptor on the plasma membrane. All right? So that is all I wanted to talk about. What if I hit escape? What's going to happen? Oh, I want to keep those. That lecture's done. So what I wanted to do was jump to the Wiley because, hey, we finished all we wanted to do on chapter 3. Were there more slides for chapter 3? Yeah, there's like 100 and something. We're only doing the first 50. So hey, let's look at these learning objectives. Your learning objective was, looking for my little, oh, okay. I can't figure out how to stop the recording. Okay. We'll cross that bridge when we get to it. Defining the cell, the 3 parts of the cell, looking at the components of the plasma membrane and their function, looking at the role of membrane proteins, talking about how this something is selectively permeable. And we talked a little bit about the electrochemical gradient. We have the passive processes. We have active processes. And then the other part of the active processes that we talked about in this lecture. Oops. Oh, there we go. All right, guys. So that is all I have to say about this as new material. you're ready for a test, man. Let's make it happen. I will see you guys on Friday to talk about this, and hopefully everything's going okay for you. All right. I'm thinking about you guys.